Parallel lines and transversals. We start this section off with a proposition. We propose that if two parallel lines are cut by a transversal, then pairs of corresponding angles are congruent. If we look at the diagram, we see that we have two parallel lines, and they're marked with red arrowheads on them to indicate that they are parallel. And the line that intersects both of them is the transversal, and the red arcs identify the corresponding angles and state that they are congruent. As of now, this is an unverified claim, and before we can accept this proposition as a fact, we must prove it to be true. So to begin, let's just do some exploration. I've got a graphing plane here, and we're going to graph a pair of parallel lines. So let's plot the points -9, -3, and -4, +7. We draw a line through it and call it line M. Then we will plot a point -2, -8, and draw a line that goes through this point, but is parallel to M. This is an example of the parallel postulate from our previous section, and we'll label it line N. Now in blue, I'm going to plot the points -5, +5, and 0, -4, and draw a line through them. This is our transversal, and it is intersecting our parallel lines at two different points, and we labeled it line P. So we should be able to identify our corresponding angles. We practiced that in the previous section, but now we want to measure them with a protractor and show that they're going to be congruent, because that is our claim that we're making, that when parallel lines are cut by a transversal, that corresponding angles will be congruent. Okay, so in this demonstration, we're going to use a protractor to measure a pair of corresponding angles. We've just finished creating our parallel lines and transversal in the coordinate plane. Now we want to take it to the next step and compare corresponding angles and see that they have equal measures. So I'm going to set up my protractor here. It's a digital protractor, so I get to really maneuver it and manipulate it so I get a good fit here. We want to get the center line of the protractor on the vertex of our angle. And we want to make sure that the edge of our protractor lines up with the transversal, so that this represents one side of the angle, and we want to measure the angle off of one of the parallel lines. So now I'm going to take my angle and swing it around to help me line it up and measure everything accurately. And I will produce an angle. It says 126 degrees. And let's see if it lines up here. 126 degrees lines up. I'll produce another angle, and I'll place it on the corresponding angle here. And we see that the two corresponding angles are 126 degrees. Since they have equal measure, they are congruent. So we can use the protractor on any pair of corresponding angles, and you'll find that they are all equal measures because the lines are parallel and cut by a transversal. So this was just an exploration using skills we know with plotting lines and using protractors. So now we will write a proof for our claim, and once we've proven it, then we can call it a theorem, and we can treat it as a geometric law. So in this proof that we've set up, you see I have parallel lines X and Y and transversal Z, and I've numbered the 8 angles formed, and you see that the parallel lines have red arrows on it to just give us a visual indication that the lines are parallel. And in this proof, we're going to prove that angle 1 is congruent to angle 3, and those two angles are corresponding angles. So we start with our given statement, line X and Y are parallel. And once we say lines are parallel, that means they have equal slopes. So that's the definition of parallel lines. And we're just identifying Z as our transversal. That was another given in the proof. And when we look at the way that angles were numbered, we're saying that angle 1 and angle 3 are corresponding angles, and that's by the definition of corresponding angles. Again, definitions are often used just to identify figures in an image. And now we can say that the measure of angle 1 is equal to the slope of line X minus the slope of line Z, and that the measure of angle 3 is equal to the slope of line Y minus the slope of YZ. And we justify this by saying that angle measure and slope are equivalent forms for measuring direction in a plane. Now, notice we've rewritten the measure of angle 3 to be the slope of x minus the slope of z. And we can do that substitution because go back up to line 2. Slope x is equal to slope y. So anywhere we see slope y, we can replace it with slope x. We've done the substitution property. And now angle 3 has the same slope representation as angle 1. Since they're the same, we can say that the measure of angle 1 is equal to the measure of angle 3. And that's using the transitive property. And once we show that the measure of two angles are equal, we can say those two angles are congruent, and that's definition of congruence. Now that we've proved this claim, we can refer to it as the corresponding angles theorem. So we have an alternate proof. We can take the figures that we've drawn with parallel lines and a transversal, and we can use what's called rigid motion. Rigid motion is when you move a part of a figure, and that part of the figure is a collection of points, and you keep everything in the same position and distance as you move it across the plane. And when we do this, that's called rigid motion. And we can use rigid motion to show that angle 1 and angle 3 are equal. So in this video, just a brief demonstration on how to use rigid motion to show that two angles are congruent. So see this angle 1, I'm going to drag angle 1 over to angle 3. Angle 1 and angle 3 are corresponding angles. We see that we have two parallel lines cut by a transversal, so we expect corresponding angles to be congruent. Rigid motion means that you're moving all of the points without disturbing their distance or position to each other across a plane. So I'm going to take angle 1 and move it across the plane, and we see that it's now replaced angle 3, and it looks the same. So you couldn't even tell angle 3 was there. Angle 1 and angle 3 are congruent because they are the same size and same shape. And we see that angle 1 can replace angle 3 and everything fits still. So that is an alternate proof using rigid motion, showing that the two angles are congruent. From angle 1 to angle 3. So now we refer to this as the corresponding angles theorem. If two parallel lines are cut by a transversal, then corresponding angles are congruent, and we can use this. So your first step is always to verify that you have parallel lines. If you can't do this, you cannot invoke the corresponding angles theorem. Then you want to identify the transversal in your image and your corresponding angles, and according to the theorem, you can conclude that those corresponding angles are congruent, which means they have equal measure, which means you can set them equal to each other when solving problems. So looking at this image, identify all the pairs of corresponding angles that are congruent with the corresponding angles theorem. Angle 1 is congruent to angle 3. Angle 2 is congruent to angle 4. Angle 5 is congruent to angle 7. Angle 6 is congruent to angle 8. Those are all the corresponding angles formed by this pair of parallel lines and the transversal. If we look at the same image and I remove those red arrowheads from the parallel lines and we have nothing telling us that the lines are parallel, then we cannot identify any angles as congruent. We can still identify them as corresponding angles, but we can't make the claim that they're equal or congruent because the theorem is not satisfied. Remember, the theorem starts by saying if you have two parallel lines cut by a transversal. If you don't have the proof of the parallel lines, you cannot jump to the conclusion and declare any angles congruent. So with this image, none of the angles are known to be congruent. We lack the knowledge as to whether those lines are parallel. And here is an algebraic example. We see that in this image, we have our two parallel lines and the transversal. We see that angle 1 and angle 2 are in the corresponding angles position, and we're given the algebraic expression for each angle. Angle 1 is 8x minus 12, and angle 2 is 5x plus 15. Let's solve this for x and for the measure of angle 1. Okay, so for this example, we're going to solve for x and find the measure of angle 1. We're going to use the corresponding angles theorem to do it. And the first thing we always want to note is that we do indeed have parallel lines. If we have parallel lines, then corresponding angles are congruent according to the corresponding angles theorem. So we see that angle 1 and angle 2 are corresponding. So we can say that the measure of angle 1 is equal to the measure of angle 2. And once we've done that, we can now substitute into angle 1 and angle 2 with the algebra we've been given. So we can say that 8x minus 12 is equal to 5x plus 15. And now we just solve for x. Now that we have x is equal to 9, we can plug this back into x for each of the expressions for angle 1 and angle 2. And because we know corresponding angles are congruent, we should get the same answer for both because they have to have equal measures. So angle 1 is going to equal 8 times 9 minus 12. We plugged in 9 for x, so 8 times 9 is 72, minus 12 gives us 60 degrees. And for angle 2, we get 5 times 9 plus 15. 5 times 9 is 45, plus 15 gives us 60 degrees. So x is 9, angle 1 is 60 degrees. We did angle 2 also, just to make sure we got the same answer. We did. That verifies that the angles are congruent, as we expected. And that's your example of an algebra problem with the corresponding angles theorem. So to continue with this pattern of first making a proposition, proving it, and then using it after it's been proven, we will move to our next claim, and we're going to say if two parallel lines are cut by a transversal, then pairs of alternate interior angles are congruent. So you see the image is similar, except the angles that are highlighted with the red arc are alternate interior angles. Again, we learned to identify these in the previous section. Now we want to make the claim that they are congruent when they are formed by parallel lines and a transversal. We're going to use the corresponding angles theorem to prove the alternate interior angles claim. So once we have a theorem, such as the corresponding angles theorem, we can now invoke it for not only solving problems, but for proving other theorems. So if we look at this proof, we've set it up. Lines x and y are parallel. Line G is a transversal. And we're asked to prove that angle 1 is congruent to angle 3 because those are the alternate interior angles. Notice that we also have angle 2 in the picture, and that's because angle 1 and 2 are corresponding. So let's work out this proof. We're going to use corresponding angles theorem to help us with this one. Line x and y are parallel. That's the given. Angle 1 and angle 2 are corresponding angles. That's the definition of corresponding angles. Again, we use definitions to identify figures and classify them. Angle 1 is congruent to angle 2. We know this by the corresponding angles theorem, which we've just proven. Now we're invoking it. Angle 2 and angle 3 are vertical angles. Again, definition because we're identifying the angle pair. And now we can say angle 2 is congruent to angle 3 because of the vertical angles theorem. We had proven that theorem in an earlier section. Finally, we can say angle 1 is congruent to angle 3 using the transitive property of congruence. Because we showed that angle 1 is congruent to angle 2 and angle 2 is congruent to angle 3, we can now link and say angle 1 must be congruent to angle 3 as well by the transitive property. Now that we've proved our proposition, we will refer to it as the alternate interior angles theorem. And again, we will invoke it to help us solve problems or with future proofs. So the alternate interior angles theorem states if two parallel lines are cut by a transversal, then pairs of alternate interior angles are congruent. The image shows you the highlighted lines with the red arrows are parallel, and that the highlighted angles with the red arcs are alternate interior and congruent. Again, you must always verify you have parallel lines. If you do not, you cannot invoke the theorem's conclusion that the alternate interior angles are congruent. So looking at this image, we have parallel lines and we're being asked to identify which alternate interior angles are congruent according to the theorem. And you should be able to state that angle 2 is congruent to angle 7 and that angle 3 is congruent to angle 6, and your justification is the alternate interior angles theorem. Now we will use the alternate interior angles theorem to solve an algebraic example. So we see the parallel lines, the transversal, and we are given a quadratic expression for angle 6 and a linear expression for angle 7. Since they're alternate interior, we will set them equal and solve for x, and then find the angle measure for angle 7. Okay, so here we have an example of an alternate interior angles theorem problem using algebraic expressions. We're being asked to solve for x and for the measure of angle 7 using the alternate interior angles theorem. And the alternate interior angles theorem says that if parallel lines are cut by a transversal, then the alternate interior angles are congruent. We check, we have parallel lines that's being indicated to us. This is our transversal. Alternate interior angles will be in between the parallel lines, that's the interior, and they will alternate which side of the transversal they're on. So we see that angle 6 and angle 7 are our alternate interior angles, and we know that they're congruent by the alternate interior angles theorem, and we know they're congruent because we've satisfied the criteria for parallel lines. So we can go ahead and say the measure of angle 6 is equal to the measure of angle 7. And now we can substitute the algebraic expressions in for angle 6 and angle 7. We get 2x squared minus 4 is equal to 7x plus 11. And now we can solve this equation for x. Because it's a quadratic, we want to get all of the x squareds, x's, and constants on one side and 0 on the other. So we have 2x squared minus 7x minus 15 equals 0. This is standard form for solving a quadratic equation. Now, because the lead coefficient is not 1, we multiply the first and last constant, and we get negative 30. We're looking for two numbers that multiply to negative 30 but add up to equal negative 7. And that would be negative 10 and 3. If you multiply them together, you get negative 30. If you add them, you get negative 7. We use the 10 and the 3 to split the middle term. 2x squared minus 10x plus 3x minus 15 equals 0. Again, you should see that negative 10x plus 3x is negative 7. So it's the same thing as this term that we have here. We just split it up. Now we can factor this. We group the first two terms and the last two terms. What do 2x squared and 10x have in common? Well, that's a 2x. You divide everything by 2x then, and that gives you x minus 5. And what do 3x and 15 have in common? Well, that's a positive 3. We divide everything by 3, and it gives us x minus 5. And to finish the factoring, we take the GCFs that we factored out, and they become one of our factors for the quadratic. And we take the repeated expression, that becomes the other factor for the quadratic. And if you were to FOIL this out, you would get back your 2x squared minus 7x minus 15. Now we set each factor equal to 0. This is the zero product property. We reviewed that in the beginning of the year. And solve each of these for x. So we see we get x is equal to negative 3/2 and x is equal to 5. We want to verify that both of those values for x are valid. That means when you plug them into the expressions we have for our angles, we do not get any negative angle measures. So let me use a new page for this. The measure of angle 6 was equal to 2x squared minus 4. And we say that when x is equal to negative 3/2, then angle 6 is equal to 2 times negative 3/2 squared minus 4. Angle 6 is equal to 2 times 9/4 minus 4. Angle 6 equals 9/2 minus 4. Angle 6 equals 9/2 minus 8/2, which is 1/2 degree. Okay, we need to check the other angle. So angle 7 is 7x plus 11. And again, we're using x is equal to negative 3/2. So angle 7 is equal to 7 times negative 3/2 plus 11. Angle 7 is equal to negative 21/2 plus, we'll change 11 to 22/2. And that gives us angle 7 is equal to, and that gives us angle 7 is equal to 1/2 degree as well. So x equals negative 3/2 is a valid answer. Let's check our other answer for x. And that was x is equal to 5. When x is equal to 5, angle 6 is equal to 2 times 5 squared minus 4. Angle 6 is equal to 50 minus 4, which is 46 degrees. Angle 7 is 7x plus 11. So when x is equal to 5, angle 7 is 7 times 5 plus 11. Angle 7 is 35 plus 11. Angle 7 is 46 degrees. So we have two valid scenarios. We have when x is negative 3/2, each angle is a 1/2 degree. It's positive, so it counts, as long as it's not 0 or negative. If it's 0, no angle exists. If it's negative, angles are defined as only positive measure. And when x is 5, we get 46 degrees for each. So there is your algebraic example with alternate interior angles and quadratic equation.
So moving forward, I'm just going to give you the remaining theorems. It is up to you as a curious student to verify these theorems using two-column proofs, as we have done with the corresponding angles postulate and the alternate interior angles theorem. You should follow the same pattern that we did with the previous ones and prove that these claims are valid and should be theorems in geometry. So the alternate interior angles theorem states if two parallel lines are cut by a transversal, then a pair of alternate exterior angles are congruent. Okay, and our final theorem is the consecutive interior angles theorem. It states that if you have two parallel lines and they're cut by a transversal, then pairs of consecutive interior angles are supplementary. So in this image, you'll notice that I'm not using the congruent angles notation. I just numbered the angles, angle 1 and angle 2. And we can say that the measure of angle 1 plus the measure of angle 2 is equal to 180 degrees. Again, we want to emphasize that these angles are not congruent, they are supplementary. Now, often you'll find textbooks that describe the consecutive interior angles theorem using a different name, and that is the same side interior angles theorem. And you can use this to your benefit because same side starts with S and supplementary starts with S. So you can say the same side interior angles are supplementary. And if that helps you remember it, great. We just want to make sure that we use the fact that they add up to 180 degrees when solving problems that involve consecutive interior angles and parallel lines. So that ends our lecture. If you have any questions, email me, watch the video again, take notes, and then do the practice.